You have already solved some systems of linear equations, 2 by 2 systems, 3 by 3 systems. And for the 2 by 2 systems, we used graphic method, substitution method, and elimination method to solve those systems. Now we are going to look at some nonlinear equations. A system of nonlinear equation just means at least one of the equations in the system is not linear. That means it's not just x to the first power, y to the first power. So look at this first system, for example. You see that x squared right there. That means it's not a linear system, even though the second equation is a linear equation. Just like with 2 by 2 linear systems, we have two methods. We can use substitution or elimination. I'll solve this first system both ways. For substitution, you have to go to one of your equations and get one of the variables by itself. We can either get this y by itself in the first equation, or this x by itself in the second equation, or even maybe this y by itself in the second equation. I think it's easiest to get this y by itself in that first equation. So for that to happen, we'll just have to subtract x squared from both sides. Then we are going to go in the other equation, and remember y is going to go home. It is now going to have a substitute in its place. So we'll copy everything else in that equation, but in place of y, we will put 9 minus x squared. Everything else we keep the same. So now we have an equation in just one variable. The difference between this and what we did with 2 by 2 linear systems is that now we have a non-linear equation to solve. It's in fact a quadratic equation. So you'll have to switch gears to, okay, how do we solve a quadratic equation? We can clean this up, distribute that negative, and it does have both the x squared term in it and the x term. So we'll just put everything on one side, simplified with x squared coming first. So combine the negative 9 and the 3. And this one can be solved by factoring. Two numbers that when you multiply, you get negative 6. And when you add, you get 1, would be plus 3 and minus 2. Set each factor equal to 0. From the first factor, you get negative 3. From the second factor, you get 2. Because it's a system, we also have to find the corresponding y. And it's easiest to just plug these numbers back in to our substitution equation. So for each of these x's, we are going to get a y. When x is negative 3, y is 9 minus negative 3 squared, which is 0. When x is 2, y is 9 minus 2 squared, which is 5. As before, we always want to write our solutions to a system as ordered pairs. So our solutions are negative 3 is paired with 0, and 2 is paired with 5. Let's solve the same system, but now using elimination method. Let me rewrite the system here. Remember that with elimination method, you try to do something to the equations so that when you add them together, one of the variables is eliminated. In fact, you can see that in this system, if I just add the two equations right off the bat, that y and negative y are going to get added, and we don't have y's anywhere else, and they just go away. So we'll just add our two equations. And just remember, you add the left-hand sides together and the right-hand sides together. So on the left-hand side, I see an x squared and nothing else in the first equation, but in the second equation, we have a plus x. The y's cancel out, plus 3. So the difference here from what we did with 2 by 2 linear systems is we just aren't able to combine those x terms, which is fine. Then on the right-hand side, we have a 9 plus a 0, which is 9. This is a quadratic equation. So I will subtract the 9 to make one side 0, and you'll see that the rest of the work is exactly the same. You can solve that quadratic by factoring. Set each factor equal to 0. Now you have to plug these into one of the original equations. Since we didn't do this by substitution, we don't have a handy-dandy substitution formula. I'll just go use my second equation because it doesn't have any squares or anything. You can also use the first equation. It doesn't matter. So we'll use this equation and we'll plug in those values of x. When x is -3, I'll plug in -3 for x in this equation. -3 minus y plus 3 equals 0. -3 plus 3 is 0. Negative y equals 0 gives you y equals 0. Or x could be 2. You plug that in here for x. 2 minus y plus 3 equals 0. 5 minus y equals 0. Y equals 5. We get the exact same solutions. -3 is paired with 0. 2 is paired with 5. So that was solving the same system, two different methods. Sometimes one method is clearly easier than another. You just have to decide. Let's also look at what the graphical representation of this system looks like. That first equation with the x squared in it is a parabola. If you get y by itself, you get y equals negative x squared plus 9. I know I wrote 9 minus x squared here because I was just trying to use substitution. I'll write it as negative x squared plus 9 so we can see the transformations. So the graph of that equation is a parabola, but with the negative means it's flipped over the x-axis. The plus 9 means it's shifted 9 units up. So you get something like this. I'm just doing a very rough graph because we're not actually trying to solve it by graphing. We're just trying to get a visual for what that system looks like. And then for that second equation, x minus y plus 3 equals 0, that one is a line. So I'll just use a different color for that. I am going to add y to both sides of that equation. That's the quickest way to get it in mx plus b form. So y equals x plus 3 means the y-intercept is at 3. Then it has a slope of 1. Go up over 1. It looks something like this. And you can see the points of intersection. One there and one there. And that's exactly what we found for our solutions. -3, 0 and 2, 5. This next system is almost exactly like the one from that first problem. All I did was I changed that power on the y. So we still have a nonlinear system because that first equation is nonlinear. As long as even just one of your equations is nonlinear, you have a nonlinear system. Now for this one, elimination is not going to work as well because I can't easily do something to this equation to get it to cancel out one of the variables here. If you try to square both sides, you can't just square each term. It's just going to be messy. So for this one, we will definitely use substitution. And I think just for variety, I will solve the second equation for x. To get x by itself, we have to add y to both sides and subtract 3 from both sides. And that means x is now going to have a substitute in the other equation. We will send x home and replace it with its substitute. So the y minus 3 will take the place of x. I'll keep the original stuff in blue. And now we have to solve this equation. Again, switch gears. You have one equation now. It's a quadratic. Y is being squared. How do I solve it? I have to simplify, put it in standard form. So we will square that y minus 3. We get y squared minus 6y plus 9 plus y squared equals 9. Clean it up. Y squared plus y squared is 2y squared minus 6y. And then the 9's cancel when you subtract 9 from both sides. You just get 0. This one we can easily solve by factoring because I can just take out 2y as the GCF. Leaves me with y minus 3. Set each factor equal to 0. If you set 2y equal to 0, you get y is 0. If you set y minus 3 equals 0, you get y equals 3. So now we have to find the corresponding x's. And for that, we will just use our handy-dandy substitution formula. We'll plug in these values for y. So when y is 0, x is 0 minus 3, which is negative 3. When y is 3, x is 3 minus 3, which is 0. So our solutions are these ordered pairs. When y is 0, x is negative 3, so you have to write it like that. And when y is 3, x is 0. We can see a graphical representation of this system. You have to know how to graph each of these equations, and some of them you do know how, and some of them you still don't know how in this class. But that first equation you should know how to graph. That first equation is a circle centered at the origin with radius 3. So I'll try to make a circle. You start from the origin, you go 3 units. Whoops, all right, that's good enough. That's the first equation. Now for that second equation, I will have to, if I want to graph it, I would have to get y by itself. So just like I did in the last problem, we'll just add y to both sides and we get y equals x plus 3. So that means you have a line with y-intercept at 3, and you go up 1 over 1, you draw the line, you get something that looks like this. And again, as you can see, the point of intersection are the solutions to the system. Because it's a system of equations, you have two variables, an x and a y. You always have to give solutions with both x and y as ordered pairs. Here's another system. Try to decide what method would be easiest to solve this system, substitution or elimination. If you're going to use substitution, you have to get one of the variables by itself in one equation, substitute in the other. Elimination, you have to see if there's a way you can manipulate the equations legally, of course, multiply both sides by something or divide by something, so that when you add the equations together, you get rid of one of the variables. Do you see what would be the easiest thing to do? We should go with elimination, because in fact, if you just add these two equations together, you see that y squared and negative y squared would just cancel out. Remember, always add the left sides together and the right sides together. So try to separate those. So when I add the left sides, x squared plus x squared becomes 2x squared. The y squares cancel. I still have a plus 3 on that side. And on the right-hand side, we have a 9. We have to switch gears now. Remember, every step of a problem is a new problem. It's its own thing you have to solve. So this is a quadratic equation. It has the x squared term, but it does not have the x term. So we can just solve this by using square root property. Get x squared by itself. And then your x would be, according to the square root property, plus or minus square root of 3. Now that we have x, we have to use one of those original equations to get the value of y. I think that first one's easier. It has fewer terms, and they have all pluses. It's easier to work with. So we will go to the equation x squared plus y squared equals 9. And first see what happens when x is square root of 3. If I plug in square root of 3 for x, I'll have to solve this equation for y. Square of square root of 3 is 3. subtract 3 from both sides, and then we apply the square root property again. So this gives us two ordered pairs right there. When x is square root of 3, y could be square root of 6. Or another solution is when y is negative square root of 6. We have another possibility for x. X could be negative square root of 3. We will repeat the process, plug in that negative square root of 3 for x, and you'll see that actually because of symmetry, we get the exact same thing. But that gives us two new ordered pairs. You have to list all the ordered pairs separately. So these are all of our solutions for this system. If you were to graph this system, you already know that first equation is a circle centered at the origin with radius 3. The other equation is a hyperbola. We haven't talked about how to graph those yet, but you will, and then you'll see that in fact they will cross, those two graphs will cross at 4 points. Here's another example, very similar to the previous one. You might want to pause the video and try it on your own first. So what method do you think would be best? You might think, oh, I can maybe get this x by itself by subtracting 3. The problem is you're not really getting x by itself. You're not isolating x in that case because you still have an x on the other side of that equation. So it might be tempting, but that's not the best way to do this. We are going to use elimination again. And you have to decide if you're going to eliminate x or y. Again, you might think, oh, if I multiplied everything by a negative 2 here, I can eliminate these. But then you'll still have an x, and then you'll have a mixture of x's and y's. You haven't really done the job of eliminating one variable. But you notice that the y only appears as y squared, and you have these two terms. You're not ready to, and that's all you have with the y's. You don't have y to the first power anywhere else. And you can't quite add them yet because that wouldn't eliminate the y squares. So we will multiply one of the equations by a negative 1. I'll just do the top equation because it has fewer terms. And that will give us, for our first new equation, we get negative x squared plus y squared equals negative 1. The second equation, we're not even changing. It's better to, when you write your system, to line up your equal signs so that you don't make a mistake when you add the left sides and the right sides. So now when we add the two equations together, negative x squared plus 2x squared is x squared. The y squares cancel out. Then I have to add, and you can even do it as scratch on the side. Negative x plus 3. What does that give me? I can combine the negative 1 and the 3, and the x I can't do anything with. So I get x plus 2. You pause, you look at your new equation. Every step is a new problem. How do I solve this quadratic equation? I would have to put everything on one side because I have both the x squared term and the x term. And we can do this by factoring. Then we set each factor equal to 0. We get x equals 2 from the first factor, x equals negative 1 from the second factor. Now, how do I get my y values? I'll just go back to the original equations, and I'll use the first equation. It has fewer terms to deal with. So we will plug in x equals 2. Then you get 2 squared, which is 4, minus y squared equals 1. Negative y squared equals negative 3. And we get plus or minus square root of 3 for y. So remember, this is 2 points, 2 comma square root of 3 and 2 comma negative square root of 3. Or x could be negative 1. You plug in negative 1 for x. Negative 1 squared is 1 minus y squared is 1. Negative y squared is 0, which means y squared is 0, so y is 0. So here's what your solutions would look like. X is 2, y could be square root of 3. or x is 2, y is negative square root of 3, or x is negative 1, and y is 0. Your systems aren't always nonlinear because you have quadratic or polynomials. Sometimes it's for other reasons, other kinds of functions, like a square root function. Well, the second equation is also nonlinear. But anytime even one of your equations, remember, is not linear, it's called a nonlinear system. And then you have to decide, are you going to use substitution method or elimination method? I think you'll agree for this one, substitution is easier. We can just get x by itself in the first equation, and then that is going to substitute x in the second equation. So let's copy what the second equation says. Copy everything there. Just send x home. X as a substitute, and it's negative square root of y. So let's see what this equation looks like. When you get rid of those parentheses, you get y squared minus 4 times. When you square a negative square root of y, the negative squared becomes positive. Square root of y squared becomes y. This is a quadratic equation. We will subtract 12 from both sides. This can be solved by factoring again. Negative 6 and positive 2 work. They multiply to give you negative 12. When you add them, you get negative 4. Set each factor equal to 0. You get your two solutions, 6 and negative 2. So then we'll just go to this handy dandy substitution formula and plug those values in. When y is 6, x is negative square root of 6, and there's nothing more we have to do to solve this. When y is negative 2, x is negative square root of negative 2. When you're solving systems, you're always asked to find real solutions only. And so we say square root of negative 2 is not a real number. We do not accept that solution. So there's only one solution that would show up on a graph, because the graph only shows real valued solutions. And that's when x is negative square root of 6 and y is 6. One last example of a nonlinear system. In this case, you have these exponential functions that you have to basically solve for because your variables are on top of the exponent. You may be able to see the pattern and solve the system as is, or for some of you, it may be easier to do a substitution first. Not the substitution for solving the system, but a substitution that replaces things that are the same, so it just makes it easier to look at. Because you see that the way the unknowns appear, the x only appears on top of e, and it looks kind of the same there. And the y only appears as a negative y on top of e in the second term of each equation. So what we are going to do, just to make this again easier on the eye to try to analyze it, I am going to let a equal e to the x and let b equal e to the negative y. This is not mandatory, but I think you'll find that it makes the system easier to solve. So if e to the x becomes a, then the system's going to be a minus, and e to the negative y became b, so that's 3b equals 1. And then e to the x is a again, so in the second equation we have 2a, e to the negative y is b, plus b equals 4. Now this is a linear system. It's a much easier system to solve. You can use substitution or elimination. I'm going to use elimination. You can eliminate a by multiplying everything in the first equation by negative 2, or you can eliminate b by multiplying everything in the second equation by 3. I think I'll do that, so I don't have to worry about negatives. So that gives us a minus 3b equals 1. 6a plus 3b equals 12. When you add the two equations together, the b terms cancel out and you get 7a equals 13. So a is 13 over 7. And then we can go back to one of these equations, whichever one you want. Doesn't really matter. I'll just use that second one again just because it has only positive numbers. So we will replace a with this number that we just found. This was our original equation in a and b, the second equation. A is now going to be replaced with its value, which is 13 over 7. Because there's only one fraction, you can try to just solve this by doing fraction arithmetic, or you can clear the fractions by multiplying both sides by 7, whichever one you want. I'll just simplify this. So again, you can multiply everything by 7 and then isolate b, or you can just subtract 26 over 7. 4 minus 26 over 7. To write 4 with a common denominator 7, you would have to multiply it by 7 over 7. I'll do it on this side. And so 28 over 7 minus 26 over 7 gives you 2 over 7. Well, we haven't finished solving the system yet. We solved for a and b. The original system had x and y in it. So we'll use our substitution formulas. I know that a is 13 over 7. That means e to the x is 13 over 7. So how do we solve for x? Just take ln of both sides. Ln of e to the x is x. Ln of 13 over 7 is, well, ln of 13 over 7. And I know that b is 2 over 7. So I'll just substitute in here for what b was. E to the negative y is 2 over 7. Again, we take the ln of both sides. We get negative y equals ln of 2 over 7. To get y by itself, we multiply by a negative. And we get the answer for y. So this system has one solution. X is ln of 13 over 7. And y is negative ln of 2 over 7. There is another way of writing this number, negative ln of 2 over 7. You can also write it as ln of 7 over 2. Because a negative can become the exponent, and 2 over 7 to the negative 1 is 7 over 2. So if you do a problem like this, and your answer doesn't quite match, and you're wondering why, they are exactly the same number. They're just written differently.